Preparation of phenol. Preparation of phenol. Phenol, as all of you know, may be called as carbolic acid. Phenol is called carbolic acid. First isolated from coal tar. And now we have few methods of preparation of phenol. Let's go through that. Number one, from chlorobenzene, the very famous Dow's process. Chlorobenzene converted to phenol. Chlorobenzene converted to phenol. Chlorobenzene fused with NaOH at a drastic condition, 623 Kelvin temperature, 300 atm pressure. You get a sodium phenoxide. You get a sodium phenoxide, which upon acidification you get a phenol, right? A nucleophilic substitution reaction, which normally a compound like chlorobenzene resists. All of you know chlorobenzene is extremely less reactive towards nucleophilic substitution reaction. They work only under drastic conditions. So chlorobenzene under drastic condition undergo a nucleophilic substitution, which upon acidification you get a phenol, the very famous Dow's process. Dow's process. All of you know there is a similar process or same procedure getting aniline also using ammonia, right? Next one. From benzene sulfonic acid. From benzene sulfonic acid. Benzene treated with oleum. Benzene treated with oleum. There will be sulfonation reaction. There will be sulfonation reaction. Sulfonyl group is better replaceable group when compared. And this when treated with the NaOH, once again you get SO3H replaced by ONA, which upon acidification you get a phenol, right? So benzene converted to benzene sulfonic acid, which is subsequently treated with NaOH followed by acidification, you get a phenol. Second method of preparation. Now the third one, from diazonium salt. Diazonium salt may be used for getting phenol. You see, aniline treated with NaNO2HCl, which is diazotization process using nitrous acid. Nitrous acid with HCl, NaNO2 with HCl, you will get an HNO2 produced in situ, and the process called diazotization. Diazotization, and you get benzene diazonium chloride. What happened to benzene diazonium chloride when treated with water or simply warming? What happens is, this is extremely unstable group present, which will be expelled as nitrogen gas, and you get hydrolysis happening, giving phenol. The compound is converted to phenol. So benzene diazonium chloride can be converted to phenol by hydrolysis, by treating with the warming with the simply warming with the water, because it is unstable. And if it is the case of aliphatic diazonium salt, at any time, no need to heat at all. At ordinary condition, upon treating with aqueous medium, you will get alcohol, right? It is extremely unstable. So that's about the three procedure. Number one, from chlorobenzene Dow's process. Number two, benzene sulfonic acid. And number three, diazonium salt. And the last one, the most important one, as most of the worldwide production of phenol is done by cumene process. All of you know cumene process. What is cumene process? Let's have a look at cumene. Cumene treated for air oxidation. Let us try to understand how you can get a cumene. Cumene can be obtained by the cheaply available material benzene. Benzene treated with the propene. Benzene treated with the propene using a simple protic acid. You can get a cumene. Benzene treated with the propene with a simple protic acid, you can get a cumene. There will be protonation, you will get carbocation attached to benzene ring, you get a cumene. Friedel-Crafts reaction. Friedel-Crafts alkylation reaction. The cheaply available components benzene and propene from the petroleum products can be converted to cumene. And this is cumene isopropyl benzene treated for air oxidation. You get cumene hydroperoxide. This is cumene hydroperoxide, which upon treated with the sulfuric acid, as you can very well understand, this part of the molecule will be out as acetone, and this OH group will be coming here, and definitely there is a suitable mechanism which we can discuss in the classes. You get a phenol and acetone. See the importance of that reaction. The cheaply available benzene and propene converted to industrially most wanted phenol and acetone. Phenol is very much wanted in the industry. Acetone is very much wanted in the industry, and that is the importance of cumene procedure. This is the method of preparation explained for the preparation of phenol in the textbook. Number 1, chlorobenzene converted to phenol. Number 2, benzene sulfonic acid converted to phenol. Number 3, diazonium salt converted to phenol. And number 4, the most important one, cumene process. Right? That's about the preparation of phenol, isn't it? Before that, we were talking about the preparation of alcohol. So many methods of preparation of alcohols we have seen. Acid catalyzed hydration, hydroboration reaction, reduction of aldehydes, ketones, esters, etc. Then reaction with the Grignard reagent. Hope you remember. Methanol giving primary alcohol, any higher aldehyde giving secondary alcohol, ketone giving tertiary alcohol, like that. So that comes the preparation of alcohols and phenols. Now you can verify working all these cases. Say for example, this question, what will be the answer for this question? A compound given treated with the NaBH4, right? What is going to happen? There is a keto group and there is a ester group, which will be reduced by sodium borohydride. Is it keto group, or is it reducing ester group, or is it both or none? 4 choices. It is reducing this group, it is reducing this group alone, or it is reducing both the group, or not reducing any of the group. I think all of you are aware of this will be reducing this group alone, not the ester. Ester group will remain as such. Ester group will remain as such. You get CO group. CO group turn CO group will turn OH group, and the rest part of the molecule remain as such, like this. So the ester group is remaining as such. Ester group remain as such, and the keto group reduced it to secondary alcohol. Try to investigate all these kind of molecules, examples given, the reactions given as examples and in text questions. Right? Of course, there are beautiful questions in the exercise part also. Next is about the physical properties of alcohols and phenols. Physical properties of alcohols and phenols. You see the boiling point of alcohols and phenols, as everybody agreed to, they have a high boiling point when compared with the other common class of organic molecules. If you compare with hydrocarbons, if you compare with alkanes, if you compare with ethers, even if you compare with aldehydes and ketones, alcohols will have higher boiling point due to hydrogen bonding. Due to hydrogen bonding, they have higher boiling point. In alcohols, the boiling point decrease with increase of branching. That is not only in alcohol, that's happening with all organic molecules. With all organic molecules, with increase in branching, boiling point decreases. That is a quite natural one, right? But when you compare alcohols in particular, compared with other hydrocarbons, compared with ethers, compared with aldehydes and ketones, remember, alcohols will have higher boiling point. Higher boiling point due to hydrogen bonding. This is the hydrogen bonding what we find in alcohols and phenols. There is hydrogen bonding involved in alcohols and phenols, which you can easily understand how they make hydrogen bonding with each other. ROH with the ROH. Again, there is hydrogen bonding. Phenol, there is hydrogen bonding. So, due to that extensive hydrogen bonding, the boiling point is much greater. You see the comparative boiling point which is measured here. For ethanol, 351 Kelvin is the boiling point, molar mass 46, while dimethyl ether, same isomer, you have 248, 351, 248, 351, 248, while alkane again much lower, 231, 231 of the comparable molar mass. If you check the comparable molar mass, 351 much greater, 248, 250 range. So 100 unit difference. Here it is 231, 10 units difference only. That is a point regarding boiling point. Boiling point of alcohols and phenols. Coming to solubility, alcohols and phenols, particularly alcohols, are highly soluble, especially the lower members, due to hydrogen bonding with water. You see the alcohol making hydrogen bonding with water. One alcohol molecule making hydrogen bonding with water. This is propanol. This is propanol. How it makes a hydrogen bonding with the water molecule? There is one water molecule over here, another water molecule here, and third water molecule here. It is making hydrogen bonding with the 3 water molecules, utilizing 1 hydrogen and 2 lone pairs in oxygen, right? So how does the hydrogen bonding comes in alcohol? Generally, if you investigate, it is ROH. Using this a hydrogen bonding, using this a hydrogen bonding, and using this a hydrogen bonding. That is what happening, right? You see the order of boiling point. You see the order of boiling point. Methanol, ethanol, propan 1-ol, butane 2-ol, butane 1-ol, pentane 1-ol. See, as the molar mass increases, boiling point increases. Methanol, ethanol, propanol, boiling point increases with increase in molar mass. With increase in molar mass, molecular attraction increases, size increases, molar mass increases, attraction increases, boiling point increases. Now you see methanol, ethanol, now propan 1-ol, butane 2-ol, butane 1-ol. This is branched one, this is linear one. So boiling point is lower. Butane 1-ol, butane 2-ol. If there was propan 2-ol, it would have been somewhere here, right? Pentanol. Coming to this one, normal butane, ethoxy, ethane, pentanol, pentanol. You see that this is normal alkane, normal alkane. Now this is ether, ether, and this is aldehyde, and this is alcohol. Alcohol maximum, alcohol greater than aldehyde. In fact, if it is a ketone, where it will come? Propanol is there. What about propanone if present? So, sorry, pentanol. There is pentanol. Suppose there is pentanone, where it will come? Will ketones be greater than this or less than this? Try to think and find out. So, alkane minimum, ether next, then aldehyde, then alcohol. If a ketone comes, where it will be? Try to think about that. Okay. Anyway, the point of discussion here it is alcohol maximum. Isn't it? Fine. Now it is about the chemical properties of alcohols. Chemical properties of alcohols. See, alcohols are giving 2 kind of reactions in particular. They are giving 2 kind of reactions in particular. Number 1, it can act as a nucleophile. Alcohol can act as a nucleophile as this is electron rich center, ROH. The oxygen is electron rich and it can act as a nucleophile. It can be attacked by an electrophile. You see, C electron rich oxygen can attack an electrophilic center. So it can act as a nucleophile, number one. Number two, protonated alcohol can act as a electrophile. Protonated alcohol can act as a electrophile. This is alcohol which is getting protonated. You get protonated alcohol. This is highly sensible to loose water. So there will be a positive center over here where a nucleophile may be attacking. So the carbon to which OH connected can turn an electrophilic center when alcohol getting protonated. Imagine alcohol is as such. As such, alcohol is nucleophilic center over the oxygen. Suppose this is getting protonated, you get ROH2 plus. This is easily subjected to remove as water. This will turn plus and will be attacked by a nucleophile. That is the point. So alcohols can behave as a nucleophilic character or a protonated. When they are protonated, it easily work as a electrophilic character. Right? And they in fact give both the type of reactions indeed. They give both the type of reactions indeed. One of the most important reaction is acidity of alcohol and phenol. Acidic nature of alcohol and phenols. Alcohols and phenols, acidic nature should be compared. Please understand the acidic nature of alcohol to be understood like alcohols are less acidic than water, while phenols are more acidic than water but less acidic than carboxylic acid. This will be the average order of acidic strength of alcohols. Somehow the nature of methanol may be somewhat abnormal, which many of you know. Methanol in some of the reactions, it will perform slightly bigger acidic character compared to normal alcohol, and sometimes it may exceed that of water also. Anyway, normally alcohol can have like this, and the order will be tertiary, secondary, primary. Primary alcohols are more acidic. Primary alcohols are more acidic, while tertiary alcohols are less acidic. If you take a tertiary alcohol, the 3 alkyl group providing inductive effect, the 3 alcohol providing inductive effect will create a polarization over here, and that reduces the ability of OH bond to break. Rather, it is interested to break over here than the oxygen hydrogen bond. We are talking about acidic nature of alcohols. So acidic nature of alcohols when compared, primary most acidic, then secondary and tertiary found to be less acidic when compared. While phenols are more acidic than water. Phenols are more acidic than water, and phenols are less acidic than carboxylic acid. Let us try to get a demonstration. If you take an alcohol versus a phenol versus a carboxylic acid, if you compare a reaction, for example, first reaction with metallic sodium, you get ROH. With the metallic sodium, you get RONA. You get RONA, liberating hydrogen gas. While you have a similar reaction over here, phenol, when treated with the metallic sodium, you get sodium phenoxide. Sodium phenoxide, liberating hydrogen gas. And if you take carboxylic acid, RCOOH, with the metallic sodium, you get RCOONA, liberating hydrogen. So reaction with the metallic sodium or reaction with something like an active metal, alcohol, phenol, carboxylic acid, it's behaving almost a similar way, liberating hydrogen gas. What about reaction with NaOH? RCOOH with NaOH, you will get RCOONA plus H2O. There is a neutralization reaction. What about phenol? Phenol. They give the similar reaction AROH with NaOH. With NaOH, you get ARONA plus H2O. So the reaction of phenol similar to that of carboxylic acid. Meanwhile, if you come to alcohol, ROH with NaOH, you don't get that reaction comfortably. So alcohols not necessarily be sufficiently acidic to neutralized by NaOH. So this reaction like this you have here and you have here. This reaction like this you have here but not here, right? Similarly, if you take a third reaction, carboxylic acid with the sodium bicarbonate, all of you know it's a very comfortable test for acids. You get RCOONA plus H2O liberating carbon dioxide. There is a brisk effervescence. There is a brisk effervescence due to the liberation of carbon dioxide. Such a reaction you don't get here. Phenol does not react with NaHCO3. No reaction. And don't have to comment on alcohols. Alcohols absolutely no reaction with NaHCO3. So alcohols, out of the three reactions, which is a clear demonstration about the acidic nature of the compounds, carboxylic acid reacting with the metallic sodium, reacting with the normal alkaline solution, and reacting with the NaHCO3, producing brisk effervescence, a comfortable test for carboxylic acid. Here you can find two reactions. Here you can find only one reaction. Is that clear? That will be a clear justification to the order of their acidic nature. Here you have one reaction, here you have two reactions, and here you have three reactions. So the three reactions demonstrated here not available here, only two reactions. So phenol is less acidic than carboxylic acid. Here you have only one reaction. Alcohols are less acidic than phenols. It's a clear justification for their relative acidic nature. Is it clear? Fine. So that is about acidity of alcohol and phenol, and a comparison being done versus alcohol and phenol. Why phenols are more acidic than alcohols? Once again, you can have a justification with the Bronsted-Lowry concept of acids and bases. ROH interacting with H plus or H2O, you are getting RO minus plus H3O plus. Similarly over here, phenol interacting with H2O, you get sodium phenoxide and H3O plus. It is a clear case to know that here the equilibrium will be more towards right hand side. Here the equilibrium will be more towards right hand side, while here the equilibrium will be more towards the left hand side, because this is more stable. This is more stable. And you find more of this reaction go to right hand side comparatively. Comparatively, here the more reaction is happening on to right hand side, because this is stable due to resonance. Due to resonance, phenoxide ion is stabilized, while here you don't have resonance. Here you have only inductive effect. RO minus, the plus I effect of R destabilizes O minus, while here the O minus character is stabilized by resonance effect of benzene ring. benzene ring undergo resonance like this. Due to the resonance, this electron density is withdrawn by the ring and thereby it stabilizes. That means phenoxide is stabilized by resonance. So what happens? Phenol is more coming to this side. What happens? You get more of H3O plus. pH relatively drops. Not quite surprisingly, it is called carbolic acid. Carbolic acid. So alcohols are less acidic than phenols, clearly justified by the stability of relative stability of the conjugate base. Relative stability of the conjugate base. Okay. Now one more point to note down is the nature of substituent on phenol. Nature of substituent on phenol. Suppose phenol has a substituent. Suppose a substituent present at orthopara position. Suppose there is a substituent present at orthopara position. Many of you are aware of the presence of electron withdrawing group at orthopara position increases the acidic character. Presence of electron withdrawing group increases the acidic character. And the property more profound at ortho-para locations, while electron donating group decreases the acidic character. So presence of electron donating group decreases the acidic character. Presence of electron withdrawing group increases the acidic character. Okay. Suppose we are comparing three molecules. Number one, phenol. Number two, cresol. Say paracresol. And number three, nitrophenol. When you compare the three molecules, very simple to understand what will be the nature of acidic character in the relative three molecules, which is most acidic. This is electron withdrawing group. Presence of electron withdrawing group increases the acidic character. So 3 is maximum. Meanwhile, here the acidic character drops. This is electron donating group. Acidic character drops. So what happens after 3? It will be 1 because no group is present. No group is present at 1. So 3 most acidic, then 1 and 2 will be least acidic. Like that. Okay. That is about a relative explanation of relative acidic strength for alcohol, phenol and ethers. If you compare the data in table 11.3, it is very much crystal clear given. You see ethanol having pKa value close to 16. All of you know, greater the Ka value, lower the pKa value, stronger the acid. Greater the Ka value, lower will be the pKa value, stronger will be the acid. That is the character. So here you can compare phenol versus ethanol. You can compare phenol versus ethanol. Ethanol 16 range, phenol 10 range. So this is more acidic. Phenol is more acidic. Here Ka value 10 power minus 10. Here Ka value 10 power minus 16 range. Not quite surprisingly, it is given phenol is million times more acidic than ethanol. Phenol is million times more acidic than ethanol in terms of Ka value. In terms of Ka value, phenol is million times more acidic. In terms of degree of dissociation, at least 1000 times. Okay. Now you see nitrophenol, electron withdrawing group. They have lower value, while cresol Cresol means methyl phenol. Cresol, electron, this is electron withdrawing group. This is electron withdrawing group, pKa value decreases, acidic strength increases. Here it is electron donating group, pKa value increases and acidic strength drop. And remember, acidic strength is more influenced at ortho-para position. It is more influenced at ortho-para position, rather less influenced at meta position. So the electron withdrawing donating effects are more profound at ortho-para position than at meta position. That's about the relative acidic strength of alcohol, phenols, substituted phenols, etc. Right? Now on to reactions, further reactions of alcohols and phenols. First one, esterification reaction. Esterification reaction. See, in esterification what happens is alcohols and phenol react with the carboxylic acid, acid chlorides and acid anhydrides forming esters. So alcohols and phenol will react with the carboxylic acid, acid chlorides, acid anhydrides in acid medium to give esters, right? Let's have a look at the various examples concerned. First of all, with the carboxylic acid, alcohol or phenol treated with the carboxylic acid. Say for example, an alcohol treated with a carboxylic acid, R dash COOH. The reaction happens in acid medium. A detailed mechanism we need to learn in the next chapter. We can discuss at the course of time. Now what happens is there will be water removed. You see OH and H out as water, and what you get is R dash COOR. You get a ester, right? That is what the reaction. So carboxylic acid, when interacting with the alcohol, you get a ester. Say for example, CH3OH. When treated with the CH3COOH, what happens? This OH and H out as water. And what do you get? CH3COOCH3. You get a methyl ethanoate. Methyl ethanoate or methyl acetate. Is that clear? Right. Suppose the reaction is happening with the phenol. Suppose the reaction is happening with the phenol. You see what happens? This is phenol interacting with the CH3COOH in acid medium. You see this OH out with the H. And what do you get? You get CH3CO O benzene, and that will be phenyl ethanoate. Phenyl ethanoate, like that. That is the esterification procedure. That is the esterification process. Okay. Now more examples available. Alcohol phenol with the anhydrides. Alcohol phenol with the anhydrides. Let's have a look at an alcohol with the anhydride ROH interacting with the RCO or R dash OH interacting with the RCO OCOR. See what is happening? It's breaking. Just imagine it's breaking over here. This is minus and this is plus. It is breaking over here. This is plus and this is minus. So this RO minus will be interacting here, isn't it? So what you get is RCOOR dash plus RCOOH plus RCOOH, like that. Say for example, if you are dealing with a CH3OH with acetic anhydride. You see, just assume it's going to break here or here, no problem. So this is minus and this is plus, just assume it's breaking here. This is plus and this is minus. This entire CH3O minus will be getting connected to this part, and the result will be CH3COOCH3. You get methyl acetate or methyl ethanoate, and the rest part CH3COOH. Acetic acid, CH3COOH. So you get methyl ethanoate and acetic acid, right? So the reaction with the carboxylic acid versus alcohol phenol, the reaction with the acetic anhydride or acid anhydride with the alcohol and the phenol, right? Or it may be alcohol or phenol with the acid chloride. It may be alcohol or phenol with the acid chloride. So I am taking alcohol or phenol, anything you can take. Say I am taking phenol this time. See, this is phenol interacting with the acid chloride, acetyl chloride, where the reaction happen in presence of pyridine. Let's see why pyridine. It is happening in the presence of pyridine. What is the net result? You see that ClH out, H and Cl out as HCl, and this HCl is withdrawn by pyridine. Pyridine is a base, and that can withdraw HCl formed. That can facilitate the forward reaction. That is the purpose of using pyridine. All of you know that. And the net will be, this part will be connected to the remaining part, and the result is CH3COO like this, and it is phenyl acetate or phenyl ethanoate, right? So carboxylic acid or acid anhydrides or acid chlorides, when treated with alcohols or phenols, you can get esters, right? A beautiful example explained, which is of industrial importance also, salicylic acid with acetic anhydride. Salicylic acid with acetic anhydride, how we get aspirin. Let's have a look at salicylic acid with acetic anhydride. This is salicylic acid, orthohydroxy benzoic acid. This is benzoic acid, and this is orthohydroxy benzoic acid. When treated with acetic anhydride, you see that. And see what is going to happen. Just assume it is going to break here, and this is minus and this is plus. It's going to break here. This is plus and this is minus. Now connect to the respective parts. O minus getting connected to this, and this O minus capture H. And what is the result? You get this one. There is COOH and OCOCH3. That is called acetyl salicylic acid. This is called acetyl salicylic acid. Aspirin. Acetyl salicylic acid. Aspirin. Acetyl salicylic acid, popular called aspirin. Aspirin, a very popular drug, a very popular antipyretic drug, analgesic drug, which was used earlier. Nowadays we don't use due to much adverse effect on the stomach and related ulcer related issues. We don't use, but aspirin and its derivatives found to be pretty good in treating for heart attack, because it has got some anti-blood coagulating action, which helps to work as various derivatives of aspirin. Like all of you may be aware of, ecospirin derivative products are widely used for heart attack related, heart diseases related issues as medicine, as the earlier use of aspirin is no more valid, in fact. Okay. So that is Esterification, a typical industrial application of esterification to give aspirin, also acetyl salicylic acid. Now you can think about, suppose salicylic acid is treated for esterification over here. What can be the product you can think about? I am not commenting anything. This is salicylic acid, COOH, and this one OH. Now we were talking about esterification over this OH group. Why can't it be esterification over this group? Suppose some methanol is undergoing esterification over this region. What will be the product obtained? And try to write that product and try to analyze the industrial importance of that product that you may try yourself. Okay, right. Now, that's about esterification. Now, next is reaction with hydrogen halide. Reaction with hydrogen halide, it's already dealt in the previous chapter. Reaction with hydrogen halide, how alcohol react with hydrogen halide. The so-called ROH interacting with HX in presence of anhydrous zinc chloride. You are getting RX plus H2O. For example, ROH when treated with HCl and anhydrous zinc chloride, you are getting RCl precipitated as a turbidity in aqueous medium. You get a white turbidity, and this in fact is used as a test for alcohols. Because the order of reactivity observed here, the order of reactivity of HX, all of you know, it is HI greater than HBr greater than HCl. That is the order of reactivity. In fact, for HI, no anhydrous zinc chloride is required. Zinc chloride is in fact used as a catalytic agent to break the carbon-oxygen bond, which is not essentially required if you are using HI. That is number one. Number two, what about the order of reactivity for alcohols? You may be remembering tertiary greater than secondary greater than primary. So for a tertiary alcohol, if you do the procedure and this reagent, it is called a Lucas reagent. Lucas reagent. If you take a tertiary alcohol, upon addition of Lucas reagent, you get an immediate turbidity, because the reactivity is greater. If it is a secondary alcohol, you get turbidity only after 5 minutes. 5 to 10 minutes you get turbidity. While primary alcohol, you don't get a turbidity unless it is heated. It is taken as a test for primary, secondary, tertiary alcohol. It is a test for primary, secondary, tertiary alcohol. Imagine you have 3 test tubes given with the 3 alcohols in the test tube. Test tube 1, test tube 2, test tube 3. It contains a primary alcohol, a secondary alcohol, a tertiary alcohol. We don't know in which test tube. We can make use of Lucas reagent. Lucas reagent added here, nothing happens. Lucas reagent added here, nothing happens. And now the Lucas reagent added here, immediately you get a white turbidity, and that will be tertiary alcohol. While you get a turbidity over here after 5 to 10 minutes, that will be a secondary alcohol. While you don't get a turbidity over here unless it is heated, that is a primary alcohol. It's a very comfortable, simple test for distinguishing primary, secondary, tertiary alcohol. And now one question, is it applicable to all primary, secondary, tertiary alcohols? I would say no. It is applicable to simple alcohols only. If you go for a bigger alcohols, imagine you are dealing with some 10 carbon alcohol. If you are dealing with 8 carbon alcohol, 10 carbon alcohol, 12 carbon alcohol, bigger number of carbon atom alcohol, if you go, probably this test may not be applicable. The test introduced by Professor Luca of California University is very comfortable for detecting simple alcohols. If you go to bigger alcohols, the test may not be comfortable. You may think, what is the logic behind? A very simple logic. Why Lucas test is not effective in determining primary, secondary, tertiary alcohol in case of bigger alcohols? A simple logical answer you may try to identify. Okay, so that's about the Lucas test and the reaction with the HCl. In fact, this reaction, you know, as a process producing RCl, it is called a Gauss process. Gauss process. As a process producing RCl from alcohol, it is also known as Gauss process. So that's about reaction of alcohol with the HCl and anhydrous zinc chloride. Reaction with the phosphorus trihalide, that also we are learning in the other chapter. Reaction with the PCl3, reaction with the PCl5, right? You will get RCl. PCl3, when you deal in particular for bromine iodine, we have to take a red phosphorus with the halogen, because PBr3, Pi3 can be prepared only in situ. They are unstable. So reaction with the PCl3, okay. Reaction with the PBr3, Pi3, we are generally taking red phosphorus with the bromine or iodine, and PCl5 will give you the reaction comfortably. So reaction with the PCl3, PCl5, etc. all that we are learning in the previous chapter dealing with the reaction of preparation of alkyl halide. Alcohol with the HCl, HBr, NABr, Ki, Lucas test, Gauss process, reaction with the PCl3, PCl5, reaction with the red phosphorus and bromine, red phosphorus and iodine, PBr3, Pi3, and most importantly, maybe you remembering reaction with the thionyl chloride, alcohol reacting with the thionyl chloride. Very important one, no? How important? How important the reaction of alcohol versus thionyl chloride? You are getting alkyl chloride. In fact, you get alkyl chloride almost pure, because the byproducts are gases, and a comfortable reaction for producing alkyl chlorides only in the laboratory. Why not alkyl bromide? Why not alkyl iodide using thionyl system? Think. Now, another important reaction, dehydration of alcohol. Dehydration of alcohol. Just have a look at dehydration of alcohol. Alcohols undergo dehydration, means removal of molecule of water. What do you get? You get alkene. Are you getting only alkene? No, it is a temperature influenced procedure. Okay. Now, how on treating with the protic acid? What a protic acid? It can be concentrated sulfuric acid, it can be phosphoric acid, it can be catalyst such as anhydrous zinc chloride or alumina. Most important thing is temperature, definitely, because temperature influences the reaction products obtained. Okay. Now see the reaction. When alcohol heated with a protic acid, you can see OH and H, water is out, and you get alkene, a double bond is created over here. You see, ethanol with the sulfuric acid, this is very, very important, 443 Kelvin temperature. If you maintain 413 Kelvin temperature, you will get ether. So temperature is very important. So ethanol, when heated with the concentrated sulfuric acid at a temperature 443 Kelvin, you get ethene. If you deal at 413 Kelvin, you get ether. If you do it below 400 Kelvin, you will get a salt of sulfuric acid, like that. There also we can understand a primary, secondary, tertiary. This is a secondary alcohol, pretty easily dehydrated. This is a tertiary alcohol, again pretty easily dehydrated. So the order of dehydration, tertiary maximum, then secondary, then primary. Tertiary alcohols are easily dehydrated, then secondary, and then primary, like that. Now let us try to understand the mechanism involved in dehydration. Mechanism involved in dehydration. There are 3-step operation. Step 1, step 2, step 3. I will demonstrate the 3-step operation dehydration procedure involved in alcohols. Suppose we take CH3, CH2OH heated with the sulfuric acid. We get CH2 double bond CH2 liberating water. This is what the process. What is the reaction involved? The reaction involved is step 1. CH3 CH2OH is getting protonated. It is getting protonated. Okay. And now what is the result? You get CH3 CH2 OH2 plus. You get this. This is called a protonated alcohol. Protonated alcohol. Okay. Now the second step procedure. Second step procedure is the actual dehydration process. Protonated alcohol can easily undergo dehydration. It can easily undergo dehydration as this bond will break and water is out. You get a carbocation. You get a carbocation. So first step, protonation. Second step, removal of water to get a carbocation. And third step, deprotonation. Third step is deprotonation. What is deprotonation? You can see the carbocation undergo deprotonation. You can see this hydrogen, this bond will break and electron shifted to carbon-carbon, and this H is out as H plus, and you get CH2, double bond CH2, that is ethene. So step 1, protonation. Step 2, dehydration, and step 3, deprotonation. So step 1, protonation. Step 2, dehydration. Step 3, deprotonation. Okay. And you can easily investigate and find out the procedure. What you find is just somewhat opposite to what happens in hydration of alkene producing alcohol. During acid catalyzed hydration of alkene producing alcohol, there are 3 steps. Protonation, addition of water, deprotonation. Here it is protonation, removal of water, deprotonation. Similar procedure. Okay. Yes. So that's about the dehydration process involved in alcohol. Next is oxidation of alcohol. Oxidation of alcohol. In fact, oxidation of alcohol means basically removal of hydrogen. That is oxidation of alcohol. It is in fact a dehydrogenation process. It is dehydrogenation process. This is alcohol. This hydrogen and this hydrogen is removed, and what you get is a carbonyl compound. A carbonyl compound. Many of you may be remembering a primary alcohol, you will get a aldehyde. A secondary alcohol, you will get a ketone. The most easily oxidizing is primary alcohol. Primary alcohols are easily oxidized to aldehyde, from there to carboxylic acid. You see, a primary alcohol can undergo easy oxidation. It can undergo easy oxidation. RCH2OH undergo easy oxidation. You get RCHO, aldehyde, and which in fact again easily oxidized to carboxylic acid. In fact, you know, the speciality is nothing but the number of carbon atom remain same. Suppose we are starting with the ethanol. CH3 CH2OH. First step oxidation, you get ethanol, and the further oxidation you get ethanoic acid. You see, 2 carbon, 2 carbon, 2 carbon. There is no difference in the number of carbon atom. Sir, then what about others? Others, there will be a difference. Suppose you are taking a secondary alcohol. CH3 CHOH CH3. Point number 1, it is not easy to oxidize. Primary alcohols are easy to oxidize, number 1. Secondary alcohols are not easy to oxidize. They are oxidized under elevated conditions. So So they can be oxidized under elevated conditions where you will get CH3, COCH3. You get a ketone. So primary alcohol, you get aldehyde. Aldehydes are easily oxidized to acid. Secondary alcohols, not easy to oxidize. If you oxidize, you get a ketone. And further, ketones cannot be easily oxidized to carboxylic acid. And if you try to oxidize again under highly drastic condition, if you try to oxidize, you can see it will break here. And this part of the molecule, you will get acetic acid. And this part of the molecule will turn formic acid, which finally turn to carbon dioxide since it is elevated condition. Now you see, we are starting with the 3 carbon. You get a 3 carbon ketone. Finally, you get 2 carbon acid. So number of carbon atom finally obtained in the acid will be less. That is the point. So primary alcohol, number 1, easily oxidized. You get aldehyde. No change in carbon atom. That is further easily oxidized to carboxylic acid. There is no change in number of carbon atom. Okay. What about a secondary alcohol? Secondary alcohol, not easy to oxidize. If you oxidize, you are going to get a ketone. From there also, oxidation is really tough. If you try to oxidize, you get carboxylic acid with a lesser number of carbon atom. And a tertiary alcohol cannot be oxidized under ordinary conditions. A tertiary alcohol cannot be oxidized under normal conditions. Right? That's about oxidation of alcohols. Various examples are given here. You can see primary alcohol converted to aldehyde and then to ketones. There is one important point. You can make use of anhydrous CrO3 to stop the oxidation at aldehyde point. You see that primary alcohol oxidized to aldehyde using anhydrous CrO3. Anhydrous CrO3 will help you to stop at aldehyde stage, not going to acid stage. There is another very important one, maybe you are aware of, PCC. PCC is very, very important one. PCC, pyridinium chlorochromate. Pyridinium chlorochromate, 1:1 ratio of pyridine, HCl and chromic oxide. When mixed, you get a complex, pyridinium chlorochromate, PCC. PCC can also oxidize a primary alcohol to aldehyde. It won't further oxidize. And PCC has got something special also. What is PCC speciality? It is selective oxidation. PCC give selective oxidation. It does not affect unsaturation. The double bond will be kept intact. Unsaturation will be kept intact. That is something special about PCC. Is it clear? What is PCC? Pyridinium chlorochromate. 1:1 ratio of pyridine, HCl and Cr2. So that is about oxidation of alcohols. As I said, tertiary alcohol do not undergo oxidation reaction. Suppose you try at a drastic condition, the bonds will break and you get alkene and different kind of products, and finally you may land up with carboxylic acid with even lesser number of carbon atom what you find than in secondary alcohols. In primary alcohol, carbon atom remains same. Secondary alcohol, carbon atom will decrease. Tertiary again will decrease if you go at elevated conditions. Now one important another reaction is reaction with hot copper catalyst. An alcohol, especially volatile alcohol vapors passed through heated copper or heated silver. There will be a dehydrogenation process. See what is happening? A primary alcohol when heated with the copper catalyst or silver catalyst. So vapors of primary alcohol pass through heated copper 573 Kelvin, you get aldehyde. Releasing hydrogen. What about a secondary alcohol? Secondary alcohol in a similar way, you get a ketone. Again releasing hydrogen gas. Say primary alcohol, when heated with the copper catalyst, you get aldehyde liberating hydrogen. A secondary alcohol heated with the copper catalyst, you get a ketone liberating hydrogen. What about a tertiary alcohol? A tertiary alcohol, in a same way, upon heating with the copper or silver, you can see there is not dehydrogenation, there is dehydration giving alkene. There is dehydration giving alkene. Is that perfect? So reaction with the copper catalyst, heated copper catalyst, that is another important reaction. It is dehydrogenation, and a tertiary alcohol giving dehydration process. Okay. There are certain points being given like this inside the box. So that is the toxic level, toxic effect of methanol. What is the treatment procedure for a person if he is affected by, all of you know, methanol when consumed by a person. A small quantity, it will cause sudden effect on the eyesight. Eyesight will be lost immediately. That is number one. Number two, a greater quantity may cause death because methanol is poisonous. Ethanol is used in the beverage drinks. Ethanol is used in beverage drinks. Preparation of various hot drinks and all. While methanol is toxic. So when methanol is contaminated, the first immediate effect is eyesight is lost, and the subsequent consequence will be death. You see, the toxic effect is basically, it is not methanol. Basically, methanol is not creating the issue. Methanol in the body undergo oxidation, converted to methanol, and from there to methanoic acid. That is toxic. That causes poisonous effect, and the person dies. What if the person taken to the hospital, if it is affected with the methanol content? You know what the treatment basically given is nothing but ethanol will be injected to the intravenous injection given as ethanol. Ethanol will be given as an intravenous injection straight to the blood. Thereby the person may recover. Why? Because in the body, methanol undergoing oxidation is the issue. Okay. Now, what happens when the person affected with the methanol, when taken to the hospital and intravenous injection given as ethanol, what happens is, in the blood, ethanol content will increase. Please understand, oxidation of ethanol is 25 times faster than methanol. In our body, oxidation of methanol and ethanol happen in different rate. Oxidation of ethanol will happen 25 times faster than methanol. So when ethanol is injected into the blood, oxidation of ethanol will pronounce, and oxidation of methanol will be suppressed. And by the time ethanol is oxidized, methanol will be excreted through urine, and hence it can be it can save the life. Such certain points are dealt over this paragraph. And now the discussion is reactions of phenol. Now it is on to some important reactions of phenol.